Welcome to our channel Edu9. Here we are discussing a property of subgroup. What is that? The question is, intersection of two subgroup of a group is again a subgroup. We have to establish that. Is the result also for union? This is our second part. For the first part, we are first of all deduce the result, then for the second part. We consider that G0 is a group and H and K are two subgroups of that group G. Now we have to prove that H intersection K is always a subgroup of the group G. For that, we have studied the necessary and sufficient conditions in the previous video, as there are two necessary and sufficient conditions discussed there, but we are going to use the second theorem, that is the last theorem of that video, where we have studied only one condition of the necessity. Now that condition was, if we considered two elements A and B from set H, which was the subset, that is the statement was, I am discussing here, if G0 be a group and H be a non-empty subset of G, then two elements AB in H, if implies A0 B inverse belongs to H, then H will be the subgroup of the group G. It was the necessary and sufficient condition. Here we are going to use this result. For that, we consider two elements A and B from H intersection K. Since A and B both are intersection in the H and K, this must imply that A and B is in H, also it is in K. We all know that H and K are subgroups of the group G. So from the necessary and sufficient condition, we can conclude A0 B inverse belongs to H and A0 B inverse belongs to K. From that, we can see that this element is in H as well as in K. So A0 B inverse is also in H intersection K. Therefore, from the necessary and sufficient condition, it is clear that H intersection K is a subgroup of the group G. Now the question is the result true for union? The second part of our question. No, the result is not necessarily true always for the operation union. Sometimes it may hold, but sometimes it may not hold. That is, in general, we can say that the statement is not true for union. Let us see some example. Suppose we consider a group G, that is Z plus. 2Z plus, we all know that 2Z plus is a subgroup of Z plus. That is why H 2Z plus is a subgroup taken, and K 3Z plus is also a subgroup of G, which is also taken. We know that 2 is an element of 2Z, 3 also is an element of 3Z, and from the definition or from the criteria of union of two sets, it is clear that 2 and 3 both will belong to H union K, that is ultimately 2Z union 3Z. That is, 2Z union 3Z is the collection of all even numbers and the multiples or the factors of 3 also. But if suppose we consider that the union H union K, that is 2Z union 3Z, is a subgroup of G, therefore all the properties of subgroup will be satisfied. That is, the closure property is also have to satisfy. But if closure property satisfied, then 2 plus 3 must belongs to 2Z union 3Z, but which is a contradiction. Why? Because we know that 2 plus 3 means 5, which does not belongs to 2Z union 3Z, because we know that 5 is not an even number and 5 is not also a multiple of 3. Therefore, it does not belongs to 2Z, it does not belongs to 3Z. Therefore, 5 must not belong to their union, that is the union of 2Z and 3Z. So closure property is not satisfied for the union in this particular case. So we can conclude from here that H union K is not a subgroup of the group G. But similarly we can go through another example, that is G is Z plus, H is 2Z plus and K is 4Z plus. But here H union K means 2Z union 4Z. 2Z is the collection of all even integers and 4Z is the collection of all integers which are multiple of 4. That means 4Z itself is a subset of 2Z. Then 2Z union 4Z means ultimately 2Z. So we know that 2Z plus is a subgroup of the group Z plus. Hence here H union K is a subgroup of the group G. So we are going through two examples where in one particular example we have seen that H union K is not a subgroup, but in another example we have seen that H union K is a group. Now the question arises easily that for which condition union of two subgroups becomes a group. This is our question. So let us see how this problem is solved, and we have to find out the condition for which H union K forms a subgroup. We are going through that in the next theorem. The statement is G naught be a group and H and K are subgroups of G naught, then H union K forms a subgroup of G naught if and only if either H is a subset of K or K is a subset of H. Any one of these two must hold. So first of all we considered that H union K is a subgroup of the group G. Now we have to prove that either H minus K is empty or K minus H is empty. Because H minus K is empty implies that K is a subset of H, and K minus H equal to 5 implies that H is a subset of K. For that we go through the contradictory method. If possible, let H minus K is non-empty and K minus H is also non-empty. If H minus K is non-empty, then we can find out at least one element A belongs to H minus K. Since A belongs to H minus K, therefore A must belongs to H, but A does not belongs to K. Similarly, we can find out an element B in K minus H, which implies that B must belongs to K, but B does not belongs to H. Since A is in H, therefore A must be in H union K. Similarly, B is in K implies B is also in H union K. We have considered that H union K is a subgroup of the group G. Therefore, all the properties of group must be satisfied. Hence, AB belongs to H union K implies A not B belongs to H union K due to the closure property. And from this we can conclude from the property of union that either A not B belongs to H or A not B belongs to K. Clearly, if we consider that A not B is in H, then also we have A is in H. From that A is in H and A not B in H implies A inverse not A not B. How can we get this? Since A is in H and H is a subgroup of the group G, therefore inverse of that element A must be in H. Also, the closure property holds implies the composition of A inverse and A not B must be belongs to H. Due to the associativity from here, we can apply on it that A inverse not A, not B implies E not B. Ultimately, B belongs to H, which is a contradiction because due to our assumption, we have stated that B does not belongs to H. Similarly, B belongs to K and A not B belongs to K implies A not B not B inverse belongs to also K. From that, there we can obtain A belongs to K, which is a contradiction because we have already stated that A cannot be in K. Thus, we have arrived up to contradictions. The contradictions is due to we have possibly let that H minus K is non-empty and also K minus is non-empty, which is not possible due to that contradiction. So either H minus K is empty or K minus H is empty. Hence either K is a subset of H or H is a subset of K. So due to this condition only H union K will be a subgroup. And if H is a subset of K, that is the converse part of the theorem. H is a subset of K, then H union K must be equal to K because K is the larger than H. So H union K will return the value of K. K is a subgroup of G. Again K is a subset of H. When K is a subset of H, then H union K will be H. It is also a subgroup of G. Thus, if we compute these two possibilities, then we get H union K as the subgroup of the group G. This is our required result.